I'm from the research unit in bioinformatics, Rhodes University, South Africa. And I will be talking about the malaria-causing parasite Plasmodium falciparum and resistance to the anti-malaria drug pyrimethamine. So malaria continues to pose a serious public health challenge, and of the 5 parasite species that cause the disease in humans, malaria due to Plasmodium falciparum happens to be the most devastating. And the lack of an effective or an efficient vaccine over the years to this parasite has made prevention partly reliant on the use of prophylactic treatment with sulfadoxine pyrimethamine, which is a combination therapy. And the pyrimethamine component of this drug acts as a competitive inhibitor of the parasite enzyme dihydrofolate reductase, or DHFR, which is involved in parasite DNA synthesis. There is widespread resistance to sulfadoxine pyrimethamine, and resistance to pyrimethamine is mediated by 4-point mutations within the active site of DHFR, with the effects of mutations aggravating as mutations accumulate from a single mutant to quadruple mutants. So we used computational methods to understand how these mutations affect the behavior of DHFR in the presence and in the absence of pyrimethamine. So to do this, we applied the following methods. We applied the following methods to all the systems, that is the pyrimethamine, the wild type and mutant systems. But for this presentation, I'm going to limit our findings to the wild type and the most resistant system, that is the quadruple mutant. So looking at free energy landscapes, we realized that pyrimethamine binding affects the conformational dynamics of the wild type, as it was seen to populate distinct conformational basins compared to when pyrimethamine was not bound. And this basins had high energy barriers between them. And also a look at the binding free energy revealed that the mutations disfavor the binding of pyrimethamine, as it was seen to have higher binding free energy when bound to, in the mutant species. And then we further looked at dynamic residue network analysis, where we realized that the active site region of this enzyme was a high communication area with respect to inter-residue communication. And this was seen by high bitterness centrality values for residues in this area. And then we further looked at differences in bitterness centrality values between the pyrimethamine bound and unbound systems. And this revealed key residues differences between the wild type and the mutant systems. And we believe that this offers a novel way of probing into the resistance caused by mutations in this parasite. To know more about this, or if you want to discuss more about this, my poster is number 21 today, and will be A33 for the 386 presentation. Thank you.